No nation which expects to be the leader of other nations can expect to stay behind in this race for space.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and thank you for your support on Patreon. We appreciate you. If researchers in Japan are right, the world is about to change, and we might soon be a fusion-powered society, with advanced ion propulsion spacecraft, flying routinely from the Earth to the Moon and back. This could not come at a better time, as the acidification and warming of the Earth's oceans has reached a tipping point. We must always be cautious, of course. We have been disappointed many times. I'm looking at you, Dr. Diaz. This is retraction number 2. Scientists do sometimes jump the gun, and no case is more famous than that of Pons and Fleischmann. These two scientists were working on something called condensed matter nuclear science, also called low-energy nuclear reactions, and better known, at that time, as cold fusion. These two researchers, Pons and Fleischmann, made headlines when they reported the possibility of nuclear reactions occurring at or near room temperature in a laboratory setting. This is not the same technology as electrolysis, where hydrogen is split from oxygen in water, though that step is necessary in the reactor to make hydrogen or deuterium fusion fuel available. It is also different from hydrogen fuel cells, like those used in the Apollo moon missions and some vehicles today. These recombine pure hydrogen and oxygen to generate electricity. LENR, on the other hand, refers to nuclear reactions that occur at or near room temperatures, typically within metals like platinum, palladium, or nickel, without the need for the high temperatures and pressures associated with traditional nuclear fusion. No billion-degree plasmas, no superconducting magnets. Some reactor designs use plain hydrogen or protium, while others use the heavier isotopes of hydrogen called deuterium, or even tritium. Deuterium is found in heavy water, and there are 33 grams of deuterium in every cubic meter of seawater. The Earth's oceans contain about 1.386 billion cubic kilometers of seawater. That gives us 45.7 billion metric tons of deuterium available to Earth. But how can we get two hydrogen or deuterium nuclei close enough together for fusion to occur, without high temperatures and superconducting magnets? The 1989 reactor, designed by Pons and Fleischmann, used a palladium electrode immersed in heavy water. Applying electricity to the electrode would separate the deuterium from the oxygen, and the deuterium would then be absorbed into the palladium metal. Hydrogen loves getting into metals, and is actually a problem with hydrogen-fueled rockets. This is called hydrogen embrittlement, and is discussed in this lesson. The scientists applied power to their tabletop apparatus, letting it run for several weeks. It stayed at about 30 Celsius all that time. Then suddenly, it spiked to 50, without any change in the power input. The researchers were thrilled, and they were convinced that they had succeeded, since a device putting out more energy than is going in is generating power from somewhere. They announced to the world through the media that they had solved cold fusion, generating a massive media response around the world. Let's look at how these devices like theirs are designed to work. Here you see a device from Superwave Fusion, courtesy of Black Box Technology. There are links in the description. This device has two types of electrodes. The cathode is seen here. It will carry the negative charge, and this one is made of palladium. The anodes can be seen here, and in this design they are made of platinum. Sensors carefully track the temperature of the solution, and the temperature of the cooling water, which is in an external jacket, and the electrical power going in. When a current is applied across these two electrodes, while they are immersed in heavy water, with an electrolyte to carry the current, because pure water makes a good insulator, the heavy water gets split apart by electrolysis. When this happens, an extra electron stays with the deuterium oxide pair. The new negative deuterium oxide ions are pulled toward the positive electrodes, while the positively charged free deuterium ions, which is actually just a nucleus, are pulled toward the negative electrode. The deuterium oxide ions give their electron to the positive electrode, called the anode, and can then split into non-ionic hydrogen and deuterium, or the deuterium oxide can combine with another deuterium to make heavy water again. Free oxygen will form a gas molecule and bubble out, as will some free deuterium. This process continues, and positive deuterium ions start to build up on the surface of the negatively charged palladium cathode. The palladium atoms form a lattice. Hydrogen, and even the larger deuterium, is small enough to travel into the matrix of most metals. Some of these ions will pull electrons off of the palladium and then share it with another deuterium ion, forming deuterium gas which bubbles away. Others will pack further and further into the metal matrix. As this process continues long enough, the cathode gets saturated with deuterium. Now superwave pulsed the power going into the cathode, causing it to flex and distort, packing in more atoms. As deuterium ions get close enough to each other, for a long enough period of time, their quantum probability waves should overlap, and because of quantum tunneling, they can teleport through the electromagnetic barrier of their like charges and get close enough for the short-distance strong nuclear force to take over. This extremely powerful force is between quarks, and it slams the two nuclei together, forming a nucleus with 2 protons and 2 neutrons. This is helium, and it bubbles out. Each of these fusion reactions releases 24 million electron volts. This is dissipated as heat and raises the temperature of the electrolyte solution. If enough heat is produced, you can get more energy out than you put in, and you get helium gas as a byproduct. The fusion reaction produces 10 million times more energy than simply burning hydrogen gas with oxygen. The trick is getting enough reactions to occur. When Pons and Fleischmann observed an unexplained and substantial excess heat production during these experiments, they believed it could only be attributed to nuclear reactions occurring within the palladium lattice. When they announced this to the public and the news generated significant excitement in the scientific community, their claims came under scrutiny. It turned out that Pons and Fleischmann had gone public before doing something that all scientists should do. Get independent verification of your results and reproduce the experiment with a different team. The scientific community quickly became divided over these claims. Some researchers were unable to replicate the results, leading to skepticism and doubts about the validity of cold fusion. Nothing makes the public happier than offering them something new and wonderful. Nothing makes them turn on you faster than taking it back. By not following through on the methods of science, Pons and Fleischmann failed to realize that they had accidentally created a capacitor effect. Their device had stored the electrical energy going in over weeks, and when it was saturated, had released it all at once. While this failure did not disprove the theories behind cold fusion, the controversy surrounding their work destroyed the reputations of Fleischmann and Pons. They faced intense scrutiny and criticism from their peers, and their careers suffered as a result. Fleischmann in particular experienced professional setbacks, and he moved to France to continue his research in a less hostile environment. In subsequent years, both scientists largely withdrew from the public eye and continued their research with significantly reduced visibility. Although they maintained their belief in the validity of cold fusion, the broader scientific community remained skeptical, and funding anything related to cold fusion became almost impossible in America. But in Japan, while they realized that Pons and Fleischmann had erred, they also felt that the theory itself was sound, as they continued working at several universities.
We support the cold fusion research just because there is something unknown apparently in it. And I think the right attitude for the scientist is to look for something unknown, unveiled.
In 2011, a massive earthquake struck Japan and damaged a large nuclear reactor complex at Fukushima, creating a nuclear catastrophe. Mr. Hideki Yoshino was very affected by this disaster. A successful entrepreneur in other industries, he started and funded a company called Clean Planet Incorporated and hired a team of brilliant engineers and scientists to work on a practical fusion reactor. Clean Planet uses the symbol QHe, which stands for quantum hydrogen energy. These scientists were aware of theoretical work that was continuing to be done elsewhere. This is Dr. Edmund Storms, a nuclear scientist from Los Alamos National Laboratory. Let's listen to what they had found at Los Alamos by 2012.
We've spent 24 years proving to ourselves first and then to the world that this is real. It's a physically real phenomenon. Now the problem is we have to convince ourselves and the world how and why it works. Nothing about this violates conventional theory. It adds to it. This is a new, undiscovered phenomenon.
So when it occurs in hot fusion very rapidly, the energy comes out in one big burst. That is, let's say they're deuterium, they come together momentarily and then they blow apart immediately in different combinations of neutrons and protons, carrying the energy with them. And so they go boom, boom, instantaneously, and the energy comes off as energetic particles. In cold fusion, they come together very, very slowly, and the energy goes off as photons, gradually, as they get closer and closer together. That's the distinguishing characteristic, and that's what makes cold fusion truly unique as a nuclear reaction. That slow interaction is not the kind of interaction people have experienced in the past, nor have much understanding of theoretically.
The more ways in which nature has to do something, the easier it is to occur, and the more often it occurs in nature. This occurs in nature very, very seldom. And it's very, very difficult to duplicate. So therefore, it must be something fairly rare and therefore very unique. And therefore, it says that nature really only has one way of doing this. And unless you have precisely that arrangement, that reactive environment, it's not going to happen. It requires a significant change in the material to occur. And that getting that change in the material has been the real big problem to make the effect reproducible. Right now, we're creating that environment by accident. We just throw a bunch of stuff together, and a few places at random happen to have the right combination of materials and relationships to one another to work. So most of the samples, maybe less than 1%, are active. The effect does not occur throughout the sample. It occurs only in special, very rare, randomly created regions in the sample. I call this a nuclear reactive environment. Presumably, the more of these sites are present, the more energy you'll be able to make. These samples would have had only a few of these active sites, and these samples would have had a large number of active sites. This becomes a probability distribution, showing that the probability of having a large number of sites were very low, and the probability of having a few sites were very high. And of course, this extrapolates to zero, having a very high probability. And that's why it's been very difficult to reproduce. I assume that something changes within the material, and I call that change the creation of the nuclear reactive environment. It has to be something that is universally present in all of the experiments that work, no matter what method is used, no matter what material is used, no matter whether it's light hydrogen or heavy hydrogen. Now, what are the characteristics of the nuclear reactive environment? Well, we know a few of them. We know that you have to have deuterium or hydrogen in that environment. We know that the higher the concentration in that environment, the faster the reaction goes. We know that something in that environment is capable of hiding the Coulomb barrier of hydrogen or deuterium. We know that something in that environment also is able to communicate the energy to the lattice rather than have it go off as energetic particles. So we know just from the way in which it behaves certain overall characteristics, but we don't know the details yet. But when I say, okay, let's talk about the nuclear reactive environment, I'm saying let's talk about where those details are located in the material. We want to look where we expect that material to be located. I expect it to be located on the surface. The challenge is to figure out what about the surface is universally related to a sample that makes excess energy. When people use solid pieces of it, all except for the last few microns of the surface are totally dead. So all you need is a few microns of palladium on something else. And I put a few microns of palladium on platinum. It works just as well as a solid piece. But after examining hundreds of these photomicrographs by other people and by myself, the only thing I could see was common to all
all experimental methods and experimental conditions were cracked.
In hot fusion, you overcome the Coulomb barrier by brute force using high energy. In cold fusion, you overcome it by lowering the Coulomb barrier using electric charge. So you have to have a condition in which the electric charge is suitably large, and cracks have the potential to produce that kind of condition.
Well, that seems crazy because for a long time in the field, people felt that cracks were bad. They allowed the deuterium to leak out of the plating.
And we see that happen because if you put some of this material that has the cracks in it in a liquid, and you can see the bubbles of hydrogen coming out of those cracks.
And so they were ignored, or people were trying to avoid them. And what I propose is that the crack has to have a particular size. And when it has that size, it allows the nuclei of either a deuteron or a proton to come into that and set up a series of, let's say, proton, electron, with the electron being between each of the nuclei, thus hiding or reducing the Coulomb barrier. Well, the size of the crack is something that will have to be determined. They have to be small enough that they would not allow the hydrogen molecule entry, because we know the hydrogen molecule does not produce a nuclear reaction. They have to be big enough that a single nucleus of hydrogen can go in there and be retained and not interact with it in such a way as it would in a chemical state. So I'm guessing something in the less than 10 nanometers.
Cracks always start small. Cracks always start at the size that would be nuclear active, but only for a short time.
The holes themselves are not the active, they only give you the indication that that stress reorganized the surface. What I'm saying is that stress also produced the nanocracks in the walls of these holes. And that's where you have to look to find the genie of cold fusion.
The nuclear active environment is proposed to be a nano-sized gap that hosts a unique form of hydrogen. While large spaces in cracks allow hydrogen to escape the material, tiny nano-sized gaps are small enough to retain a single nuclei of hydrogen in a covalent chain called a hydroton. Subjected to the high concentration of negative charge in the walls, the electrons shared by the hydrogen nuclei are forced into a more compact state with an average smaller distance between nuclei. But what happens to create a nuclear reaction?
Whatever it is, has the ability to initiate a number of different kinds of nuclear reactions. One makes helium, heat, another one makes tritium, another one does transmutation. So there's a variety of things that can happen in that environment.
Now, all behavior using all isotopes of hydrogen can be explained by a single basic mechanism operating in a single nuclear active environment.
I mean, that would be a lot to expect for something so unusual as this to have a variety of ways in which it can happen. By sheer probability chance, there's a crack form. It has to have the right size. And then because of diffusion, they start building up a concentration in the crack.
Hydrogen, when it gets into this gap, forms a covalent chain, which I call a hydroton, which releases Gibbs energy, and that stabilizes the gap.
Hydrogen can form a chemical compound that has lower energy than any hydrogen anywhere else in the material. So the hydrogen migrates there, forms this compound, and because that compound is more stable than any other, it cannot decompose without that energy being reapplied to the hydrogen in order to get it out of there.
Because that's occurring in a chemical atom, it follows all the rules of a chemical reaction.
That narrow crack would have a very high concentration of electron or negative charge on both walls, which would force the hydrogen into a structure that I believe
would help hide the Coulomb barrier and would help the resonant process take place. All right, once that builds up to a sufficient number, something triggers it. That can just be the normal temperature vibrations because everything's at an atomic level is vibrating.
But because it has a linear structure, it can start to vibrate such that these two come together, these two further apart, these two come together, and so forth.
All right, so these things start to vibrate in line. And when they do, because you have charges moving, you have the prospect of photons being generated.
When these two come together, they find themselves too close. They have too much energy, too much mass for the distance, because they're on the way to having formed a fusion product.
Now the system knows that if it collapses, gets closer and closer together, it will gain energy because the end product is a nuclear product that has less mass than the sum total. So it knows that that's the direction to go. So it just keeps giving off photons.
Finally, enough's given off that each time they get a little closer, they give off a little bigger photon.
Each time it gives off a photon, it collapses a little more, another photon, a little more, a little more. Meanwhile, vibrating, photons are streaming out. Finally, the last photon goes off and it becomes a deuteron because the electron that was between them gets sucked into the final product.
But there's hardly any mass energy left over at that point, so this becomes stable, or if not, gives off a very weak gap.
And then that's deuteron now there. Now, that deuteron, if there happens to be another proton or another deuteron in there, it can start the process all over again. If another deuteron happens to be there, then it can make helium. Or if a proton happens to be there, it'll make tritium. The deuterium then has a choice. It can diffuse out, in which case it'll be replaced by a proton, more likely, because that's what's in the general environment. Or it can stay there and another proton comes in and it starts to fuse and it makes tritium instead. Well, it is symmetrical as these things bounce. It isn't just when they bounce this direction they give off the photons. When they bounce this direction they give off photons also. So these things are bouncing in a symmetrical way. Each time they go this direction they lose mass and then they come back together and lose mass. At some point they've lost enough that these two guys don't bounce and they stick together, and then these two guys over here stick together.
And so the question is, where during that process do they recognize that they have too much mass and have to get rid of it? When you do it by hot fusion, that's done very, very quickly and it overwhelms this process. I'm proposing that this is the unique feature of cold fusion. This is where cold fusion differs from hot fusion.
Cold fusion is slow, it's methodical. Because it occurs over a period of time, the energy has time to get out in small quanta. Crack is not destroyed. The crack is a manufacturing tool. It's just simply there, and atoms go in, fuse, get the products diffuse out, maybe, or they stay there. More stuff fuses. It just simply is an assembly line of the fusion process. That crack becomes attractive, and it's also attractive because it's very difficult to produce, and it's outside of the thermodynamic characteristics of the material. In other words, cracks can occur in any material regardless of its thermodynamic properties. That's why cold fusion was essentially rejected by people who were educated and had experience with hot fusion, which plays by entirely different rules.
Clean Planet wanted to try this theory, so they created nickel-copper nanoparticles, dramatically increasing the active surface area. Here you can see that the copper is 2 nanometers and the nickel is 14 nanometers. Then they could compress these particles together, creating tiny cracks between them. And according to their recent announcement, this technique succeeded, creating a reactor called Icaros, with an energy density 10,000 times higher than methane. This is much, much higher than any known chemical reaction, and means that enough nuclear reactions are occurring to make up the difference. The reactor can create temperatures up to 1,000 Celsius, and was ran continuously at about 935 Celsius for over 500 days. Icarus is 63 centimeters tall, about 2 feet, and weighs only 4 kilograms. According to their research, 18 grams of deuterium, that's a little more than the mass of 7 American pennies, will power an average American home for a month. Clean Planet is working on making boilers for commercial use. And if this announcement is true, we could be on the cusp of a dramatic shift for human civilization. Low-energy nuclear reactors could be just what we need to move off Earth, because supplies of deuterium fuel on Earth, the Moon, and worlds throughout the solar system is almost infinite. Something to think about. Thanks for listening, and stay safe at Astra Pro Terra.